Okay, let me see the write operations of your SRAM. So as like the previous case, here also we are assuming that the memory contains some pre-stored data. So we can see that this is, we can say that Q, this is become Q bar. So we can say that Q is equal to 0. So we are assuming that here the logic 0 is available and Q bar is equal to 1. Here we can able to have logic 1 is going to be getting available at this point. And here what we have, the WL is equal to 1, so that we can say that your M5 will be in on condition, M6 will be in on condition, so that the bitline bar can be act as can able to access the latches what is it available in your SRAM. And as like the previous parameters what we seen, the BL bar is going to be, the BL bar and BL is going to be acting as a input, right? And now we are seeing that we make sure we are making that the BL bar is equal to ground. That means it is going to be 0, right? It is going to be a 0. In the case of analyzing the write operations, let me forget about what is it. Let me forget about the your precharge capacitors over here to analyze your write operations. So let's go through what is it happen when we talk about this. Let's see that now 1 is going to be available. So now since it is 1 at the Q bar, at the point of BL bar is equal to 0. So it's offering the low impedance path. This path is going to be grounded, so that since M6 is in on condition, so this path is going to be offering into the low impedance path. So previously of a low impedance path, what will happen here, the M1 is in the on conditions. Can you see that? M1 is in the on conditions. Why? Because here is 0 and the previously the logic 1 is present. So because of the logic 1, your M1 is in on condition and M2 is going to be in the off conditions over there. But since this BL bar is 0 grounded, so all the charge which is available at the point of this Q bar is going to be getting discharged through this low impedance path. So because of it, what will happen, this will become 0. So since it is become 0, we can see that M1 is going to be start to fall in the category where the voltage of at which M1 is going to be start to slowly slow down up to what level? It is going to be below your VTH level actually. When it is go, the below the voltage value is going to be drastically drop down less than VTH. What will happen? The M1 is become off. In other terms, to be understanding, if all the potential is going to be getting discharged at this point, so the 1 is become 0. So called M1 is in on condition, it's become in the off condition, and so called M2 is in the off condition, it is become on condition. So what we can see on the left hand side, so since this M1 is in the off condition now, so there is no any discharge is possible through which, and it's going to be offering the output open circuit. Now only M2 is in on condition, so whatever the data which is available now, the M2 is, since the M2 is on, the VDD is going to be getting supplied, so M2 is become storing the value as 1. Previously it is become 0, now it is going to become 1. See that now? The bit line is 1 we are writing now over here on the side, and this side is going to be 0 because the difference is here we connected to ground, here it is connected to the 1 over there as an input. So we can see that the Q is going to be written as a 1, right? So same way we can able to analyze for the Q is equal to 0 also to understand the write operation of a SRAM. So followed by we have a general circuit elements of your SRAM. So where we have the general array structure is going to be getting available on the center, and for each and every word line and bit line is going to be getting available. Since I already discussed, since its memory elements going to be available in the row and column structure, the row is going to be indicating in terms of the word line, and the column is going to be indicating in terms of the bit line and bit line bar. So as we seen in the read and write operations, the bit line bar, here the bit lines and bit lines bar will be always connected to the sense amplifier, and the sense amplifier is connected with the column decoder and as well as the address buffer. Accordingly we can able to analyze that what type of data of reading and writing we are going to do it over there. So through this decoder and the buffer we can able to select a particular address, right, a particular column, and through this address buffer and the row decoder we can able to select a particular column. So through which the sensing amplifier we can able to do either the data read, data in or data out. That is nothing but we can do either write operations or else we can do the read operations for your static RAM, right? There. So come to the pros and cons. So when you talk about the advantage over here, it is much faster, we know that, and low power consumption because it is made up of the CMOS devices, and creating speed sensitive cache. and no need of refresh of the memory content and power efficient also. So that is the advantage we can say about this pros. And when we talk about the drawbacks or else in terms of the limitations, it has become very expensive, right, because it is adopting the 60 transistors, right, and it's having low storage capacity and low memory density. Why? Because like every in order to store 1 bit of data, we need 6 transistors for the purpose for that to be activate that particular latch to store the data. And loss of data, when it is going to be, there is no power, because we know that SRAM is going to come under the category of volatile memory, and does not offer to refresh the programs, because once it is stored we can't refresh it back again. And more complex designs when you're going to compare with the DRAM. Why? Because for 1 bit we required 60, and you just think about that, when that number of bits going to be getting increasing to store the data, that number of transistors is also going to be getting increasing, so that the design of the design of the complexity also is going to be getting increasing, and the more number of transistors going to be occupy the more number of area. So that are all the limitations we can say when we talk about the DRAM architecture, right? Let me come to the DRAM. So the DRAM operation is very simple. When you compare with your SRAM, there is no any complexity, because we have only one MOS transistors available over here, and that to be we are using one NMOS device going to be getting available. And here we have 2 capacitors. One is on the right hand side, we can call it as your storage capacitors we have on the right hand side, and we have the left hand side, there is one more capacitors available, that is going to be acting as a reference capacitors, or else we can talk about this going to be a pre-charge capacitors according to the previous discussion. This can be acting as a pre-charge capacitance. With reference to the pre-charge capacitance voltage value, we can say that whether we are going to do operations of read or write, and how come the 1 and 0 is going to be getting stored in the DRAM, we can see it over here. And as like your SRAM, here also the word line is going to be activated for your row access, and bit line can be acting as your column access, right, for the column access. And we can say that when you're going to do the read operations again, the bit line is going to be acting as a output, and when you're going to do the write operations again, right, when you're going to do the read, is going to be acting as output. When you're going to go to the write operation, the bit line is going to be acting as a input device, as like your SRAM, right. So see that how we can able to do this DRAM operation is, we can very quickly we can recap it, because since we already analyzed the complex of SRAM to how to do the read and write here. So to do the read operations, we can see that the pre-charge capacitance CB, it having the voltage value of VDD by 2. We are assuming that the node at this point, let's say for example node A, the node at the point A, we have the potential of VDD by 2, by assuming that the pre-charge capacitors is going to be charged up to the off level of the VDD, right? And we are make sure that WL is equal to 1, because when WL is equal to 1, we can say that the transistors become on, so that we can able to access the CC, the charge capacitors. And let's see that how come we can able to do that. If CC is equal to 1, so if CC is equal to 1, that means we are saying that since it is on and bit line is also going to be getting on, we are going to do the read operation. We are assuming that CC is equal to 1, that means charge capacitor is equal to 1. What is the meaning of it? These charge capacitors are having some already stored value, so in the level of the charge of VDD. And now we can see that now this VDD is going to be accessed through this transistor, because since the bit line is going to be acting as a output to do the read operation, this will be come into picture over here. Here we have a VDD, here we have VDD by 2. The potential difference is going to be available, because VDD and VDD by 2. What we are comparing now, what is the voltage at which, whether it is greater or less than. So at this point, accordingly over here we can, assuming that this VDD by 2 is equal to V, we see that V is greater than VDD by 2 at the point over here, because this is VDD over here. So whenever the V is greater than VDD by 2, we can see that the bit line output is become VDD, because our bit line output become like this. How? This will be a V greater than VDD by 2. So we can sense that is going to be output is equal to 1 through the sensing amplifier, right. That is a process at which we can able to do the read operations, right. In terms of the other condition, in case if it is going to be output is equal to 0, what will be the condition? For output is equal to 0, the condition is going to be very simple. The V at the point must be we can say that less than VDD by 2, so that we can able to say that the output is equal to 0 from the DRAM architecture, right. So let me go for the write operation of the DRAM as like a simple way. So here we can say that the bit line is going to be acting as an input over here, so that we are feeding the input from the bit line over here, and WL is equal to 1, so that this transistor is become in the on condition. Now we are feeding the bit line is equal to 1 over here now. So what is it case over here? So let me analyzing this by through which we can able to check out your right hand side part. So when this is equal to 1, we are seeing that the charge capacitor is going to be start to get charged on this up to level of VDD, so that we can say that we can see that CC is equal to VDD, so it's getting charging. So we are saying that we are writing is equal to 1. Let's say for example here we are writing the logic 1. Let's say for example I want to write logic 0. What will happen? We can make this bit line to be grounded. So whatever the value which is stored on the previous condition is going to be start to discharge through your low impedance path, so that all this VDD value what is it available is going to be getting discharging through this ground line. So the CC is become discharging, so we can say that your value at the CC is going to be equal to logic 0. So that is a way in which we can able to do the read and write operation of the DRAM, right. So come to the pros and cons. So when I talk about the advantage, it is going to be very fast access time, because it is very simple, because we have only 1T transistors available here, and high density is possible because we can able to include the number of transistors in a multiple way if the bits is getting increasing to store the data, and low power consumption because the number of transistors is gradually reduced and it is become more cost effective. And what is the limitations? Of course, since it is a volatile, we need a power. So through constant power only we can able to do the operation. And limited lifespan, we are pointing out is a limited lifespan, because here we are making use of the capacitor is going to be the one of the major element to store the data and to store the data, and as well as to 1 and 0. In terms of 1 and 0 we are charging and discharging the capacitor, so that there will be some leakage will be possibilities available, so that we can able to say that the lifespan of storing the data is going to be very less. And we can say that susceptible to errors due to the capacitor activity. And since the charging time, it will take a charging time and discharging time of the capacitor, so it's taking its own charging time and its own time taken for the discharging, so it's required some sort of time delay will be available over here. This time delay we can make the device going to be more slower when you're going to compare with your DRAM cell SRAM cell, right. So as a summary, so far we just seen what are the types of classification of memories available in terms of volatile and non-volatile, and we just seen about how come the read and write operations can be done through the SRAM device, and how come we can able to use the DRAM for the both read and write operations, right. Thank you so much.